I would like to welcome you all in the lecture series of power electronics. In this session, I am going to discuss the operation of three-phase full converter. First of all, we'll understand why we require three-phase full converter. We know that if the application, if the power requirement, if the operating load is more than like 100 or you can say up to 120 kilowatts, single-phase full converter is not suitable because there will be more ripple content and that's not convenient to operate. And economically, single-phase full converter is not convenient if the power rating is high. At this instant, you can go for three-phase full converter. We can say that the three-phase full converter performs two quadrant operations. Also, we can say like the output ripple voltage that is 6 times of supply frequency. So the frequency range you can observe the output ripple voltage is 6 times that of the input frequency. By comparing to single phase full converter, the requirement of filter that is very less, and also the total amount of harmonics. If you compute the THD, total harmonic distortion, that is comparatively less in the case of three phase full converter. That is what for the high power application we prefer three phase full converter. Here the thyristors are turned on at an interval of 60 degree, or you can say pi by 3 radian. Okay, the firing angle you can say like pi by 3 radian. So these are the basic information about three-phase full converter. First of all, I'll be showing you the circuit diagram. Later, we can go for like a explanation with the help of waveforms. So we have the three-phase supply. Here you can connect either delta or star. Here, as you can observe, we have connected the supply in the form of star connection. And we can see there are 6 devices. So T1, T3, T5 are considered as positive group, where T4, T6, T2 are considered as negative group. The converter output is connected to the supply load. Here, sorry, the converter output is connected to load, where the rating of the load is high, around up to 120 kilowatts. Here we consider the load is considered as highly inductive load. The voltage across the load is V0, correct? So we can compute the line voltage and phase voltage from the star connection that you know, right? So this is basically the circuit diagram of three-phase full converter. Now we'll discuss how does it operate. The thing is, the devices are fired like in the following sequence: T1, T2, next T2, T3, T3, T4, T4, T5, T5, T6, then T6, T1. Like that, the device will be activated at a firing angle of 5 by 3, 5 by 3 radian. This is the basic operation of the three-phase full converter. The average output voltage across the load is high compared to single-phase full converter. Also, the total amount of distortion that is less. Also, we can say like the filter requirement is comparatively less as compared to single-phase full converter. For example, you can see if I talk about like a T1, T6, one of the cycle called a T1, T6. Okay, here at omega T is equal to alpha plus pi by 6, the T6 is already conducting and the T1 is already on. So during this interval, we can say like the conduction angle is alpha plus pi by 6 to pi by 2 plus alpha. The thyristor T1 and T6 will be conducted and the line voltage VAB come across the load. Okay, same manner, T1 and T6 that will conduct at this particular firing angle. Similarly, we can go for like a other case. Thyristor T2, when omega T is equal to alpha plus pi by 2, we can say like a thyristor T2 will be turned on and T6 is in a reverse bias immediately. So T6 is turned off due to the natural commutation. Commutation is nothing but the method of turning off the thyristor. Similarly, during the interval, we can say like the in between alpha to pi by 6 and 5 pi by 6 plus alpha, the T1 and T2 will be conducting. The cycle will be repeated. So you remember that particular firing angle and how the sequence will be activated. Firing sequence will be in this fashion: T1, T2, T2, T3, T3, T4, T4, T5, T5, T6, ultimately T6, T1. The cycle repeats. Here you can see the waveforms of three-phase converter. Here it is very clearly mentioned about the supply voltage. It's a three-phase supply. You can see VR, VY, VB, and you can write either line voltage or in terms of phase voltage. Here you can see the how the device is going to conduct. Look at this T1, T2, T2, T3, T3, T4, T4, T5, T5, T6, then T6, T1. Like that, it is getting repeated. Now we can check the phase voltage. Okay, here you can see like a VAN. Okay, VAN, then VBN, VCN. These are the phase voltage. Now we can see the output voltage, like means like VDC. Here we can see like a VCB, VAB, VAC, VBC. Like that, you can mark the output voltage. Here, the how the when the thyristor T1 is getting conducted. Now look at this. So in this region, corresponding to this particular region, the device is getting conducted. Here you can see like the thyristor T2 is conducting. Look at this. In this particular range, thyristor T2 is getting conducted. Similarly, here you can observe T5 and T6 here conducting in the reverse direction. Okay, so the output, if I talk about the load current, since it is DC, it doesn't vary with respect to time. So try to draw these waveforms for three-phase full converter. It will be really helpful for your exam point of view. Okay, so I'll be demonstrating the same three-phase full converter with the help of MATLAB. That I will do it later because this is important topic for your exam point of view. That is why I'm explaining the theoretical part. Now you need to calculate the neutral voltage. How to calculate the line voltage? Okay. So VAN, VBN, VCN. Okay, line to neutral voltage. So you can write like VAN is a sinusoidal waveform, Vm sin omega t. VBN is equal to Vm sin omega t minus 2 pi by 3. Then Vm sin omega t plus 2 pi by 3 will be the voltage across VCN. If I compute this, we can call it as a phase voltage, not line voltage, phase voltage. You know what is phase voltage? Take one line. For example, A, this is N. VAN means it's a phase voltage. If I talk about like a line voltage, we have like A, B, C, N. Voltage between A and B. Okay, that is actually called line voltage. Here, line voltage is computed like root 3 times of phase voltage. See, since it's a star connection, we need to consider like this. So I have written line voltage of the three segments. Okay, so remember it's a star connection. Line voltage is root 3 times of phase voltage. That is what you can see like root 3 has come over here. Very simple mathematical analysis. Yeah. Now we need to calculate the average output voltage. So use this formula to calculate average output voltage. Decide the upper and lower limit. Okay. 3 by pi into upper to lower limit VAB d omega t. So if you do the integration properly, you'll be getting 3 root 3 Vm by pi into cos alpha. That is actually the average output voltage. This is most important. You may get a question for deriving the average output voltage of three-phase full converter. So kindly see the limit, do the integration properly, give upper and lower limit at the variables. You are able to get 3 root 3 Vm by pi cos alpha. Now maximum output voltage. So put alpha is equal to 0. So you are able to get 3 root 3 Vm by pi. That will be the maximum average output voltage. Similarly, normalized voltage is nothing but the average output voltage to the maximum average output voltage. Take the ratio of the first these two equations. Equation number 1, VDC. This is VDM means equation number 2. Take the ratio of VDC by VDM. So ultimately, you are able to get cos alpha. Cos alpha will be the normalized average output voltage. If you want, you can use the calculate the RMS output voltage using the formula. So whenever you are taking the RMS output voltage, it should be square root. That is what I put half means square root. 3 by pi plus alpha plus pi by 2, 3 Vm square sin square omega t plus pi by 6 d omega t. Sin square theta means 1 minus cos 2 theta divided by 2. That formula you can use, then do the integration. Finally, you are able to get root 3 Vm into half 3 root 3 by 4 pi cos 2 alpha. Kindly verify once again. You can practice normally. Okay. So this is the answer you are able to get the RMS output voltage. In this video, I discussed about how does three-phase full converter operate. So what is the total power range that you can understand. Later circuit diagram I have explained. Then operation, basic operation, and how the triggering will be taken place. What is the sequence of triggering? Later you can see the waveforms and just verify how does three-phase full converter operate. Later mathematical calculation which is required for numerical and derivation. So initially I computed the line to neutral voltage. Later line to line voltage. Then I calculated the average output voltage. then maximum average output voltage. Later, I have taken the ratio of average output voltage to the maximum average output voltage. Finally, I'm getting the answer like cos alpha. Then I could compute the RMS output voltage and expression is given here. So this is a brief idea about three-phase full converter. So if you have any questions related to this topic, feel free to ask with me. I'm going to reply in the comment box. Thank you very much for watching this video. Happy learning. Have a great day.